How will our diagnostics contribute to improving the results further and eventually getting to inertial fusion energy? That's a great question. So for right now, we're continuing to provide this information that I already talked about, the number of fusion reactions that happen in each implosion, how hot the implosions get, and how tightly they're compressed, as well as contributing to the measure of symmetry. But in order to move towards IFE, we need to improve the implosions even further. We need to improve the gain. So like how we multiply the energy that we put in to energy we get out. To get there, we think we need a time-resolving neutron spectrometer. So this is something that our group has been working on for a number of years now. I'm currently leading the project to make this happen on the NIF, but it's a big undertaking which requires entirely new back-end detector technology. So it's based on the MRS concept. You still have the conversion foil, you still have the magnet system, but on the back end, instead of those plastic 039 detectors, the idea is actually originally to put a pulse dilation drift tube where you take the incoming signal, deskew it, and also stretch it out in time. So you're maybe able to make snapshots in time of a burn that's 100 picoseconds wide. So 100 picoseconds, it's let's see, how do I explain that right? It's 0.1 billionths of a second. So it's incredibly short burn time, and now we're trying to divide that into several windows so we can measure how the neutron spectrum evolves in time, so we can see how does the temperature develop during that short burn, how does the compression develop, in order to really bring the implosions to their full potential. We have to understand the time evolution as well. So that's what we're working on right now. And honestly, it's been challenging to get funding to make that happen, because it's such a challenging project and we're not 100% sure that the new ideas are going to work as planned. Typically with an NIF, you want to prove a technology before you put it on there, because it's such a large undertaking and it's really expensive just to do the engineering to install stuff. So if you don't know in advance that it's going to work, it's hard to get the funding. So that's something that we've been working on for a while and we'll continue to work. And we just actually had a new graduate student start who's working on a new concept for the back-end detector to reduce the risk, so we can take that step. Okay, so that was answering one half of your question. We think that building on the technology we have right now to a much more advanced detector is going to help. We also need to be able to turn the data around faster so that we can move towards high repetition rate. So right now, one of these experiments happens maybe once a month even, or it can happen once every couple of weeks. But in the future, we need them to happen 10 times per second, right? So we can't have the 039 detectors. We have to etch for 6 hours in sodium hydroxide and then scan under a microscope for 4 hours. It's just not going to cut it. So the other thing we're working on is upgraded MRS, which can handle both higher yields. So we're also pushing in, now that we're producing 4 megajoules out almost from the NIF, we're pushing into saturation for the current MRS. So we're working, another one of our graduate students is working on a new concept that's going to be fielded further away from the target chamber to handle higher yields, and with an electronic detector where you can read those signals electronically and directly turn around the analysis. And that's going to be helpful not just on the NIF, but as we move to future facilities where we're able to repeat these implosions faster. Simulations to understand what's going on in these implosions can use those techniques. Basically, you can run a large number of simulations and then use those techniques to aggregate the information from them to try to find ways to improve the implosions. That is a growing effort. There's a group at Livermore that's working on it. You can also use those techniques in some contexts to analyze diagnostic data, which is more directly related to what we're doing. So for example, one of the students in our group did a summer project at Livermore this summer. Livermore is the facility where the NIF is at in California, where he's taking diagnostic data from a set of activation detectors that's distributed around the chamber, and from an imaging detector, trying to combine that information into morphology. And he's using machine learning techniques for that. So it really, and this is new, right? This is something that we're just now learning how to do, which I'm expecting it to contribute a lot over the next several years.